talking about today? Stars?
I thought we'd talk about stars. Good guess, Matt. Good guess. Hello, Tyler and Kylie joining us by Zoom. That's 2, 4, 6, 8, 10. We're still missing like 4. Liam and Dante and Hunter and Bailey. Bailey never comes on Monday because she has math methods.
Okay. Yeah, she's it. I think that is fluids.
Hey, there's Liam.
Okay, she was like, yeah, I'm not going to do fluids.
All right, we're pretty much all here now. There's been a plea to move exam 1 back. I'm accepting that plea and considering it. But in the meantime, I've also posted a survey with an announcement linking to it on Canvas about exam 1. So let's talk about exam 1 real quick. Assuming that I don't accept the plea to move it back, it's scheduled for next Wednesday. I had mentioned that we would talk about when and where that would actually happen specifically. First, let me talk about format. I've been hedging about this before. It will be a paper write-out exam. There will be some define this term. There will be some explain this phenomenon. There will be some plug these numbers into this and find this value kinds of questions. So it'll be a mix of those kinds of questions. It will be open calculator, hey Dante, but not open Mathematica. So hey Hunter, but not open Mathematica. So I won't be asking you to, for instance, integrate the plot function from this point to this point or that point to that point. It will be those kinds of questions will not be asked. So that's the format of exam 1. Any questions about that? Liam? There will be a formula sheet. Yes, I can even give you what that would be, or at least the last time I gave an exam like this ahead of time, if that would be helpful. Maybe by the end of this week. Sure. Yes, there will be a formula sheet. Any other questions? Right. That's the second half of this conversation that we hadn't gotten to yet. We're just talking about the format so far. It will be in person. When, though, is TBD. Yeah.
Are we going to have like my student exam or practice exam beforehand, or should we just kind of focus on like?
Yeah, that's a good question. Probably not. But you know, the kappas are a decent thing to look at. Obviously, there are some important themes that we've talked about as we've gone through the class. So, yeah, good question. Okay, yeah. Yes.
Like several times.
Yes. No, there won't be anything that complicated. On the homework, yes. On a 50-minute or even 2-hour exam, no.
How much are you going to add in terms of time content if it's outside of class?
Yeah, that's a good question. So that relates to part 2, which is when do we want to have this exam? I sent out a doodle poll, not a doodle poll, it's a Canvas poll there's an announcement with a link to it. You can go on and it's linked on the Canvas page now. Please answer this by tomorrow evening. I should have done it by tonight. It's a 2-second poll. But the choices, so 3 choices on there. In class, next Wednesday, March 10th. Outside, that would be a 50-minute exam. Outside of class, Tuesday night, March 9th. It's 2 hours, probably 7 to 9, although that's negotiable. 2 hours Wednesday, March 10th. Outside of class, probably 7 to 9, but that's also negotiable. I don't think I could give the same exam in both of them, but the 2-hour exam will not be 2 times longer than the 50-minute exam. Does that answer your question?
Wait, what is that? I don't.
The in-class exam would have to be shorter than the out-of-class exam, but it's not going to be half as long as the out-of-class exam, if you see what I mean.
So, okay.
So you'll have, I think the 2-hour exam will give you, what's that?
So it would be shorter than 2 times the 50 minutes.
The 2-hour exam will be less than 2 times the length of the 50-minute
It's not
exam.
100% more.
It's not 100% more. That's right. There's a lot of ways to phrase that particular thing. So I think, if you want to take an in-class, I will design a test that I think can be reasonably finished in 50 minutes. I think the 2-hour exams will be easily finished in an hour to an hour and a half, right? And then you just got extra time there if you want it. That's sort of how I think about these 2-hour exams. So it's not that I think the 50-minute exam will be hard to squeeze in. It's that I think you'll have plenty of time for 2 hours. So again, there's no pressure. 50-minute exam is fine. Everybody has the same, unless you've got some accommodation, the same amount of time. It's I don't like tests to be tests of how fast you can do something. I don't like that model of giving an exam. So I think, but there's all kinds of things. And I'm technically not allowed to give an evening exam unless we're all on the same board. So the survey is 3 buttons. You can press 1 of those buttons, 2 of those buttons, 3 of those buttons. I suppose you can press none of the buttons, but that's not going to be very helpful because we need to do something. So go ahead and fill that out by tomorrow night, and we'll have more detailed conversation about this on Wednesday. Okay. Other questions about logistics like that?
Would it be in this room if it wasn't in class?
If it was in class, probably so. Yeah.
Even if it wasn't?
If it wasn't in class, we could spread out in the astronomy labs or something down the hall if we wanted to. Although there are other labs Tuesday and Wednesday night. It could be in here too, right? We all fit in here, so that would work. That's not something I had thought about though, but negotiable. Wait.
If Kylie does Wednesday night labs, it's 8.
Yeah, there are labs.
And now you have
Oh, so Kylie could not physically do the Wednesday night exam, at least if it were 7 to 9. Okay, all right, that's fine. Yeah, I was gonna send an Thanks, Kylie. All right, we could move that around earlier or later too on Wednesday. I don't know how that would work, but yeah, this is why we need to have this conversation, because I haven't thought about permutations. Okay, great.
No problem.
Great. So let's. So we have it's a double Astrobite week. It's very exciting. It's the only double Astrobite week of the semester. Bailey is going on Wednesday, and she said she'd get me her article by the end of the day. As soon as I get it, I'll post it. You can read it by Wednesday. And I think Kylie's going on Friday. And Kylie, you should get me your Astrobite article by Wednesday.
And so is the homework due tonight, right?
The homework is technically due tonight. What's that?
Okay.
I'm upset that I pointed out that it was rejuvenation day because then it got moved earlier. I'm sorry.
Would you like me to push it back to Wednesday?
That'd be great.
Technically midnight.
Well, if you did Wednesday morning.
Yeah, you can do Wednesday morning. It would take
And the
0.
I'll just push it back to Wednesday at midnight.
I don't think you're allowed to do vacation.
I'm not allowed to have it do a Tuesday at 11:59 p.m.
Wednesday is 12:01.
That's what I said, Wednesday at midnight.
Wednesday, but I'm happy to move it back to Wednesday at midnight. I don't really care.
0, 0, 0.
That seems unhelpful. I'll push it back.
One more kappa between this one and
Yeah, that's the idea, is we'd have another kappa next week. before this one's due, before the second exam. So that does start to squeeze them together. There won't be another one due this week, but there might be one due next Tuesday or Monday or Tuesday, which I'll get up mid this week. Does that make sense? Okay. That's the problem with pushing these back is fine, is that, but then they get compressed at some point. So it is what it is. Okay. Let's do an astronomy picture of the day because I thought it was pretty good today. Look at that. Right? Not bad. So this is an image of the Pelican Nebula. Don't ask me to point out the Pelican because I won't be able to. I've actually seen the Pelican in some images of this, but you have to be, I think, zoomed out and on the right and looking at it in the right, sort of filters to be able to see usually. This is an interesting thing about nebula. Why are these things called what they're called? Usually it's named by again, once you do something, it's one way in astronomy, you're stuck with it. Looking at this thing through a small telescope, what does it look like with no filters through a small telescope? That's sort of how these things get their name. And not even a small telescope, but the small telescope in the 1700s or something like that, right? These are the people who are actually naming these things. So, they don't always really look like that today, especially with these amazing views we're getting now. Anyway, this is an image that highlights the red, obviously, H alpha in emission. These are star forming regions. And the blue is actually ultraviolet coming from these very bright, hot, massive stars. And so that's the cool thing. That's one of the cool things. The other cool thing is there are these dark regions, and we'll get to a point in the class where we start talking about the interstellar medium, the stuff between the stars. But there's a lot going on, and these ionized hydrogen regions where we see this H2 emission is one of them. We now understand what all that means. But these guys, the dark lanes, are other regions of the interstellar medium that are much denser and much cooler and still have, these are called molecular clouds because they're so cool that hydrogens and molecules. So the temperature difference between, let's say, this region and this region is dramatic. This is in the tens of kelvins. This is probably in the hundreds to thousands of kelvins, maybe even. So this is where stars begin to form. There has to be a very dense region of the interstellar medium for stars to form. And then once they form, they turn on and they heat up their surroundings and they begin to clear out their gas, and then that gas starts to glow. So this is a region where you still have some regions that are probably still forming stars and others that have formed stars more distantly and have already started. You can sort of see the bubbles around some of these stars where they've cleared out the gas around them as they've turned on and just blown all that stuff away. Matthew Van
Allen. Are there any stars, so like you said, these were named by people in the 1700s. Are there any noticeable stars that have gone out since we started observing and recording stars?
No.
Because it's got to happen at some point.
Right. So stars come and go. There are things called novae, which is literally Greek or Latin for new star. And every once in a while, there are different kinds of novae, but typically it's a white dwarf and you dump hydrogen onto it and you get a surface explosion. And the thing gets a lot brighter for a little while. So this was recorded by ancient civilizations all the time. Some new star pops up in the sky, freaks them the crap out, right? That's a major thing. But then it would fade away and be gone, right? But as far as one of the stars that we know actually physically going away or going supernova, I don't think that's happened in recorded history.
Did we ever briefly look away and then look back and realize, oh my goodness, we missed?
No. Stars don't fizzle out generally. They either go out spectacularly or over the course of millions of years, right? It's not a blink and it's gone kind of thing usually. In fact, the most spectacular way for stars to go is supernovae. There hasn't been a supernova that's gone off in the Milky Way galaxy that we know of since Tycho Brahe was making observations of them in the 1600s. That's pretty long time. Sure, it's a snapshot, but there are 100 billion stars in the Milky Way. We expect for for galaxies the Milky Way size to have a supernova go off about once a century. So we're way overdue.
Does that mean that that's what we just haven't been able to see, or that
Uh,
we just
Both of those are possible.
Couldn't they just be on the like exact?
It's possible. It's possible that if it's on the opposite side of the galaxy and was behind some of these very dark, dense clouds, we just wouldn't have seen it. Especially if it were before the age of like the past 50 years, where almost the entire sky is being monitored in lots of wavelengths all the time. So we're overdue for a supernova in our galaxy.
Also, like further stars, like the light from them old, but does that not really matter because the light from them is congruent? Right? Does that make any sense?
Maybe.
So, it's like, is the
So-
whole section of time, the further away you are, you're looking. Does that make?
Yeah, sure. The further away you look,
That
it,
doesn't- Like the fact that it's all doesn't matter, still should have happened in 100 years.
that's right. That's right. Because maybe what that you meant by congruent, right? We're still seeing for every slice of the universe, no matter how far you are away, you're still seeing the same amount of time pass between those 100 years. It's just a different slice. Yeah. That's right. And the Milky Way's, yeah, well, right. The Milky Way's 100,000 light years across, right? So, but I see what you mean, but doesn't really matter, right? It's, even though we're seeing further away, further in time, back in time as we go out, we're still seeing 100-year slice in every 100 years for every one of those slices. That's right.
One last easy question. Nova are very like tenuous, right? Like you wouldn't like you would be like this coloring is only visible in aggregate from a distance, right? Or like
This coloring is only visible in aggregate for a distance.
like comparing like you don't see blue air here. You can only see the sky from when you're looking at a very thick.
Right. Well, we haven't ionized our hydrogen and it's not glowing the way this is glowing, right? So there's two things happening here. One is it would look red. In fact, if you look at this region through a telescope, it looks red
Right.
because of the hydrogen that's being the hydrogen emission. You're only seeing it because there's so much of it over such a long range
Right.
that because it's so far away, right? You're not going to see a single hydrogen atom doing its thing, but you'll see, 10 to the 20 hydrogen atoms along that column
Right.
emitting those photons.
So it's not like in Star Trek where they're flying around, it's like just giant cloud.
Yeah, that probably is a miss. Obviously, the cloud is way bigger than you're going to be able to move around it as fast as they seem to be moving around it.
Right.
And two, I don't know. The closer you get to them, the probably the less spectacular they will glow, right? Because you're just seeing the same column density. The column density that you're seeing has fewer stars in it.
Right.
So that's probably also true. Way to bring us all down. That's what you're here for. Okay, great. That's 20 minutes of intro stuff. Let's get to some questions. So we left off last time talking about, I forgot to share the screen. Apologies, Zoomers. Hopefully you were following along wherever you were on your own pod classes. Okay. I believe that, let's see. So let's just follow up. Here's the original HR diagram. We're talking about this at the end of class last time. What I didn't show you and probably should have was diagrams that look like this. This is an HR diagram, a modern HR diagram from the Hipparchus satellite. Hipparchus is the precursor to Gaia. And this is all stars within some distance limited region of the sky. So let's say out to 50 parsecs or something. And you can see, obviously, we're doing a lot better than they did in 19 teens. You've got a beautiful main sequence, which has some real structure to it, which is interesting. It's got some real width to it. These magnitudes are way better than the width of this particular line. And those are usually somewhat age, but also composition differences between stars. Real composition causing stars of the same mass to be at slightly different positions on the actual star diagram. And then you've got some giants coming up here. I'm asking you to do two things on this week's kappa set. I've given you a even better data set than this from Gaia, published last month, actually in December. And your job is to make a plot that looks like this, which is go out to a specific distance and plot everything out to that distance. Absolute magnitude versus color. And then so one's a volume limited sample where you go out to a specific volume. The other one's a brightness limited sample where you go down to all stars down to 6th magnitude EG, which is basically all the stars that are visible in the sky. To see what the differences are between this, which is the volume limited sample, and the brightness limited sample, which is actually going to give you quite a different picture. But when you're making these plots for the homework, make sure that it's a normal HR diagram. In other words, bright stars are on top, faint stars are on the bottom, hot stars are on the left, cool stars are on the right. So that's going to mean your y-axis is backwards. The small numbers are at the top because those are going to be absolute magnitudes. And it's going to mean, remember how this works, that we're going from small magnitudes to large magnitudes in the V minus R that you're going to be plotting. If you do that, you should see a plot that looks kind of like that. You'll see some other cool things there as well, because Gaia goes way deeper and can see way fainter things. And that fills out the bottom of this diagram quite nicely. There's a lot of things down here that Gaia got that Parcos didn't get, which is fine. Okay. What else do I have here? Right, here's the theorist's HR diagram. Where should these stars be when they reach the main sequence? And again, this is a physical number, effective temperature. This is not a magnitude, but it's like a magnitude, and then it's a log luminosity over luminosity of the sun. And you can see, again, if you've got luminosity temperature, that gives you a radius for free. And you can connect lines of constant radius on this log. This is actually a log plot. And you can see where all of these stars actually are on the HR diagram. From O stars, mid O stars, all the way down to the M stars. Yeah. Anything else I want to say about that? Oh, so you can see that even it isn't obvious as you move up and down the main sequence whether these stars are getting larger or small. But it is true that the top of the main sequence stars are quite a bit larger than the bottom of the main sequence stars. So this is, again, a factor of 100 in stellar radius between these dashed lines. So that's not a small effect. Okay, and this is our next thing that we're talking about, which is luminosity class. I believe I set up at the end of Friday, because class is Friday. Our goal, so we can distinguish between all of these spectral classes based solely on the spectra that we get from those stars, right? And that's part of the point. Take ratio of spectral lines of various types and be able to match a spectral classification here and put it right on where it should be. The question is, can we tell the difference between these stars and these stars based solely on their spectrum? Because those line ratios should be about the same with the same surface temperature. So the answer is we can. So the answer is lines get, as you move up on HR diagram, the spectral lines get broader. And this is as the radius goes up. Oh, I'm sorry. This is down. This is exactly wrong. As you move down in the HR diagram, the spectral lines get broader. So as radius goes down, the acceleration due to gravity, the force of gravity on the surface of that object goes up, assuming the mass isn't changing dramatically, and the pressure goes up. So these stars will have a higher acceleration due to gravity, lowercase g on the surface, and therefore higher pressure than these guys are. These guys should be pretty fluffy. The outer parts of their stars are puffed way out. And so the pressure is just lower out there. That would be a normal thing. And so this, you may seem like that's a small effect. It's actually not a small effect at all. These are luminosity class. These are all A0 stars. These are the temperature equivalent of Vega, right? These are 10,000 Kelvin stars, every single one of them. And you can see how much different, again, the line ratios, again, this is an A star, so these are hydrogen lines, and it dominates the spectrum. But the ratios of these hydrogen lines to some other helium are all about the same, but the spectra themselves look dramatically different as you move from what is a supergiant well above the main sequence to the main sequence to well below the main sequence. And so this is one of the ways that you can distinguish between where they are. You can see how much broadened these lines get. So we'll talk about pressure broadening in a bit, but what's basically happening is the more pressure there is, the more fuzziness there is on those energy levels, and the more width those actual lines have for that very region. They get sort of pressure broadened. The lines themselves and the energy levels aren't quite as well defined. Interesting. So you can define, and we do, luminosity class. Thusly, and we're Roman numerals because we've already got letters and numbers, so we need some other axis. Again, remember the letter and the number is just a temperature thing. This is the other axis of luminosity now, so we're going to use Roman numerals for this one. And of course, interestingly, luminosity class 5 is a dwarf, and by dwarf we mean main sequence star. 4 is subgiant. 5, no, I'm going the other direction. 3 is giant. 2 is right giant. And 1 is super giant.
I see on that other chart that our sun just falls into the giant category.
No, our star is a G25. It's definitely main sequence, right in the main sequence.
So the area between lines weren't all because the bottom is white dwarfs, and then the line above that says super giant.
Line above what? Where are we talking about?
Go back to maybe right there. So,
oh, I see what you mean. No, this wasn't to suggest that this whole bin is giant. Okay. It's to suggest that this region here is giant. And this region here is super giant.
Okay. I kind of took this these
right.
sections.
No, that's a good point. That's not the case at all. In fact, this is the weird thing. These luminosity classes, especially 5, incorporates pretty much all luminosities that a star could possibly have. Right? Luminosity class 5 just says it's on the main sequence, which could be anywhere from here to here. And it's really just proximity to the main sequence. How far above is it the main sequence? The 1s are pretty much all right here. But 2s kind of are sloped, 3s are kind of sloped. It's not and that's why there's no specific, it's a spectral classification difference, right? And that can lead to, different specific luminosity differences at different temperatures for where those actually fall. It's really proximity to the main sequence. 5, if you're on the main sequence, you're a 5. If you're above the main sequence, you're going to be one of these. How far above the main sequence is going to tell you which one you are. But there are main sequence stars that are more luminous than giants, right? Here is a main sequence star that is more luminous than this giant down here. So luminosity class is a thing, but it's not a true all ones are brighter than all twos, or brighter than all threes, brighter than all fours, which makes it kind of confusing. Within a different particular spectral class, that's true, but you can't compare those luminosity classes to other spectral classes and expect that to be true all the time. So that's a good point. Right. So that was my next point. Since these are based on spectra, this is how these are defined, right? There are your templates. And when you're, again, it's the 1920s, you're doing this, you're just looking at templates and you're trying to match them where they are. And once you define the template, that defines your A05, A05, or A04, or A03. And so where that specifically goes on the main HR diagram, they weren't concerned about. They were just concerned about getting a scheme to classify these things that was repeatable and was measurable. So that's the real point of this. So specifically, luminosity classes 4 and 5 have a huge range in the actual luminosities of which they operate. So that's where we're at. Oh, here you go. This is so here we have this is somebody's from 2000, no, maybe 2000. Diagram showing where these luminosity classifications actually go on the HR. So here we've got main sequence. They've actually got a sub-dwarf thing here, which, if you're getting technical, some people include a sub-dwarf. These are the white dwarfs down here. Here is 4, right? 4 and 5 are basically the same until you get, down to classification in the A's, and then they kind of branch off. 3s isn't really a thing also until you get to 10,000 Kelvin and cooler, right? So it's really, and then 2. So it kind of is that these are moving across, but you can, there are 3. This is a 3 right here. Make it really close together as you go up. And so the difference between a B5, 2, 3, and 5 is very small and not really all that important. It's, it's when you get over here that there's huge ranges in those. So just take that grain of salt with you as you're going. Luminosity classes is much more important for the cool stars than it is for the hot stars. Okay. Cool. All right. So this HR diagram is really important, as I said before. Think the periodic table of the astronomy world in importance. Okay. Chapter 9 is stellar atmospheres. This is really important chapter, but it's boring and it's complicated and it's hard to understand without a context for what you're talking about. So we're going to talk about a couple of concepts in chapter 9, but we're more going to move on quickly to chapter 10, and then I'm going to say several times over the next few weeks, oh, remember that stuff we skipped in chapter 9? Here's a result from chapter 9. If you're interested in how it was derived, you can go back and see it. But I think it will make more sense to talk about it in the context of where we're actually using it and why it's important later on, rather than just in the context of stellar atmospheres. But stellar atmospheres are incredibly important because, all the lines that we're seeing come from the stellar atmosphere. They're not the most important part of the star, which is the interior structure that makes it up. but they are the part of the star that we observe and see and can measure. And so how that boundary layer works, where the light's coming out, is really important. So we'll skip to the observational part. What is it that we observe of stellar spectra, and how is it important, and how do we use it? So skip to observational, and I will come back to others as we need it. Okay, so this is like spectral lines. This is already section 9.5. The shapes of absorption line. We've already talked about pressure broadening, but it turns out the shapes of those lines can tell you other things besides just the pressure of the gas. And so let's talk a little bit about the shapes of absorption lines. Shapes of absorption lines gives info about the environment in which they're created. Okay, so how do we measure the strength of a line? This is an important thing to do. And there is a specific way that astronomers tend to do this. So this is the stellar continuum, right? If there were no absorption line there, we would expect so this is a normalized continuum. So we usually normalize the continuum. So in other words, we divide through by a smooth spectrum that goes through the spectrum itself. And instead of worrying about some Planck curve distribution, if you divide a star roughly by its expected Planck distribution, you'll get a normalized curve where everything's one. And that's what this is, except it's more complicated than that because no stars really are Planckian, so you have to do some fit. Anyway, it's not important. We set the continuum to be one, and that makes it easier to do lots of things. So you've got a line in here. How's it going to look? It's going to look maybe like this. Maybe it's a Gaussian, maybe it's not a Gaussian, but it's going to have some depth, right? And it's going to have some width. So how would you go about measuring the strength of this line, right? This is, again, intensity is a function of wavelength of the spectrum, right? So the way we measure the strength of this line is the area under the normalized curve. And by normalize, I just mean set the continuum to 1. So we call this an equivalent width. Let me write down a formula for it, and then I will explain why it's a width. W, we usually call it W, the integral of FC minus F lambda divided by FC d lambda, where FC is the flux of the continuum, and F lambda is the actual flux of the star as a function of wavelength. So FC minus F lambda basically just flips this upside down and makes this a positive Gaussian for the purposes of measuring its continuum, measuring its area. And this normalizes it. And then, this normalizes it. And then, this is just a normalization factor, really. And then you're integrating over wavelength, right? So why do we call it an equivalent width? It turns out that this is equivalent to an area that If these two have exactly the same area, then this is the equivalent width. It's the equivalent width in nanometers or angstrom or wavelength space that has the same area but goes all the way to 0 and is square on both sides. So this has units of wavelength, right? These fluxes all have units, but they cancel out because we're taking ratio, and the only units over here are from this length or this lambda. So the units, oddly, on the area of this is a wavelength, is a single distance unit, because this axis has units of normal lengths, and this is some continuized, non-united factor. Make sense? So the formula doesn't really all that important. I'm not going to be asking you to calculate this. I wrote it down just so you can see how it's related to this. Equivalent width is the area under this curve. It's really all you need to know what it is. And it's an area, and it's a width. It's given in nanometers. Like, so I could say, 100 milliangstroms or something would be an equivalent width. And a deeper line would have a larger equivalent width, and a shallower line, or even narrower line, would have a smaller equivalent width. So it takes both of those things into account: how deep it goes and how wide it is. Nanometers, angstroms, whatever you want to use. Milliangstroms, nanometers. No, that's not going to work. Okay, this is the width that the line would have. If it were square. And I really mean rectangular, had square sides, and extended all the way to 0. Okay, we often will define some parameters of this, like the full width half max, or the FWHM. Well, nobody says FWHM. They'll write FWHM, but we'll say full width at half max. And by that, so the maximum, and that's a minimum, because we're always kind of thinking about this upside down. This is the maximum. So the full width at half max is take half of that value and take the full width all the way across that spectrum. That would be the full width at half max. So it's a measure of, like Gaussian sigma, of how broad that line is. So if you specify both the full width half max and the equivalent width, you can do a pretty good job of drawing what that line is going to look like down here, assuming it's fairly Gaussian, which it isn't always. Right, so this is the part of class where I usually will break out a spectrum and show you some real spectra of real stars. But it turns out that over the past year, the analysis program that I had used to do all of that stopped working on any Mac laptop. So, and I haven't, I was looking at it before class and didn't have time to figure out a new way to do that. But I will try to figure out a new way to do that by Wednesday and actually show you some real spectra and show you some differences in these equivalent widths and show you how I measure an equivalent width, although that's going to be harder because that I knew how to do on the old one and I have no idea how to do on the new one. And how, even show you some binaries and things like that. And show you how some of the full width have maxed very dramatically from one started when you look at real data. So you can look forward to that on Wednesday. But let's think about this. Why do lines have width at all? Shouldn't they be infinitely narrow? And shouldn't it be the case that since the energy level of this, whatever line it's coming from, this is a transition between two energy levels on an atom, and that energy should be fairly constant. Why is there any width to this? We can, if you want to make that a question, sure, we can brainstorm. What do you think?
Doppler shift as well as
Doppler shift. How is a Doppler shift going to affect things?
stars moving away with
Okay, right. So starting moving away, all of its lines, all of its. So if you have a specific, that will move the whole thing left or right, but it shouldn't make it broader. It's a good idea though. Rotation. So that is a way that you can get a single star to have a broader thing. If a star is physically rotating, then some of it's blue shifted and some of it's red shifted, and that is going to make this broader, no doubt. That's one reason. Yes. That's the second on my list. Well, let's just list them now. Doppler broadening. You were right for the method, but wrong on the application. This is rotating stars. Let's get some others. What do you think? I already mentioned one of them in today's class. Ooh, that's an interesting thought. What would the interstellar medium cause?
Like if they're traveling through like regions of different density, like bounce around and stuff.
Yeah, so that shouldn't change the wavelengths of photons after they've been emitted, right?
Okay. Yeah.
So it could certainly rob us of some of those photons as they get absorbed. So it shouldn't change the wavelengths of the light that comes to us from that star. You could imagine that it might add, other lines or maybe to this line in a different way that might change the broadening. That's a pretty small effect. But good guess.
Could it be as opposed to rotating, but revolving around something else? Would that make any difference?
Yeah, it can. So if you're in a binary system and doing this, that's again going to move all of them at the same time, and they're going to move back and forth. So, but at any given moment, it shouldn't change the breadth of this line, but it will cause the whole thing to move back and forth. Yeah, I talked about pressure broadening. Remember? So pressure broadening is simply the higher pressure the gas is under, the more that tweaks the energy levels of the atoms that are in, basically. And that's one that I'm not going to talk about, but is important, and I've already talked about. The other one's not all that obvious. I'm actually going to talk about two of them. This is one of them, and this is the other one is well, we could list a dozen of these probably if we wanted to, but there's two important ones that I want to talk about. And this is the first where I'm at on time. I got 2 minutes. I'm going to at least start this one. Natural broadening. So yes, it turns out that there should be exactly always the same energy difference between electron energy levels, but that has to be modulo the uncertainty principle, right? We cannot know the true energy difference between levels modulo how long that thing is actually going to last. So that actually will limit the true ability to know specifically for any given atom what those energy level differences are. So Heisenberg uncertainty principle actually plays a role here. HEP, if the lifetime of a state is finite, there is an inherent uncertainty in the energy of that state. So how does this work? Delta E is about equal to h bar over delta t, where t is the lifetime of that state. And of course, h bar is h over 2 pi. The shorter the lifetime, the larger the uncertainty in that actual lifetime. So we know that E equals hc over lambda. That's just the energy of a photon at a particular wavelength. We know that delta E is, this is simply propagation of uncertainty, delta E over delta lambda times delta lambda squared, square rooted. This is just what delta E is, going to propagate uncertainty. The definition of that. So we also can take the partial of this with respect to wavelength. Del E del lambda is negative hc over lambda squared. Oh, I'm out of time. All right, we'll finish this derivation on Wednesday of what the natural broadening actually gives us. And why there is some of this is always observational, right? Our instruments also sometimes can't pick up a single line as finely as the line actually is. So, but there are reasons for the stars themselves for those lines we brought up.
The lines change much, just like the cyclic nature of like, say like our sun. No.
Doesn't change much at all. Like if you look at a flare or look at some sort of sunspot, there might be some changes that happen. But if you just look at the sun over the course of its 11-year cycle, even not much has happened at a random point on the sun surface.
Having pressure buttons. Is that like there being alternative paths for the energy to be like instead of the electron going as so like inside into the